I don't know if that's seconds.
Oh, yeah, that's what
Okay, so what's velocity? Okay, units meters per second, but what is it in terms of position? Velocity is the
Magnitude and the direction.
magnitude and direction. It's a vector, true. But if I want to describe it as a rate of change, what would I say? Velocity is. Okay, so there's a way. We could do it as an equation. We could say it that way. We could say that average velocity is equal to displacement over time, right? If we want to use words, we could say the same thing by just saying it's equal to the rate of change of position. And then we ought to add at the end, with respect to time. But oftentimes, if we don't say that, if we just talk about a rate of change in physics, what do you suppose is implied about what we're comparing it to? Well, yeah, but so we technically should say this is the rate of change of position with respect to time, right? But a lot of times we'll just be lazy and say it's a rate of change of position. What must we be implying if we're being lazy? That if we don't, yeah, okay, time is almost always going to be the independent variable, right? The input variable. So if we ever just talk about something as being a rate of change, it's implied that we're comparing it to time, right? Make sense? Okay, so then there's our definition of velocity. So what's our equation definition for acceleration?
Velocity over time.
Okay, so change in velocity over change in time. Or if we wanted to write that as, or say it as a rate, we'd say what? Rate of change of
velocity
with respect to time, right? Okay, good. Okay, good. So we've done a lot with that. You guys have done a lot of work with some kinematic stuff where you've dealt with fairly complex situations where you're given some information and you've got to solve for a kinematic quantity, right? That's good. Okay, but really all we've done is we've just like, if you're going to be a writer, all you've really done to this point is maybe learned the alphabet, right? And maybe some grammar or something, right? You haven't really learned or maybe just the alphabet almost, right? You haven't really done anything with it, right? I mean, sure, we've looked at some situations and we've described some things, but motion is really most interesting when we're talking about the cause of motion, right? And so here we've talked about velocity, we've talked about acceleration, but my question to you now is, what causes the acceleration? And you probably know the answer.
Gravity.
Okay, those are all sort of good answers, but there's one answer that would really encompass them all. Well, you're jumping the gun a little bit. Kinetic energy we will talk about, and it's related to this, but what is it? Force. Yeah.
No, don't even.
So that was dangerous. Wasn't it?
That was dangerous.
Yeah. Okay, so all right, so the kinematics, we know how to describe the motion, but the cause of the accelerated motion in the first place is a force, right? So what's a force? Something. Say it again. Something that is exerted on something else. Okay, I'll buy that. Let's see if we can get this down to as simple a definition as we can. If you wanted to describe force to your second grade nephew or something, what would you tell him?
I'll push you down.
Okay, it's a push. Okay, it could be a push. Really, there's only two things it could be. It could be a push or a pull. That's it, right? That's a force. It's a push or a pull, right? What's an example of a push? Well, push would be if you push somebody, or right now the table is pushing up on this plate, right? Yeah. Okay, what's an example of a pull?
If you pull it off.
Gravity.
Okay, I guess I could grab it like this and pull it up in the air. Gravity is pulling it, right? Okay, so a push or a pull. We'll get more quantitative than that, right? And we'll describe that in more detail. But really, in short, that's what a force is. So the thing you got to remember about forces, they're pretty simple, but at the same time, there's some parts of forces that might be even a little bit counterintuitive, talking about forces. Forces have to have what we call in physics agents. So forces are produced by agents, right? So, for example, if I'm holding this remote control, is there a force acting on it?
Yes.
My hand is providing a force, right?
Yeah.
So the push on this remote control, the agent of that force is my hand, right? Everybody agree?
Yeah.
That's, in other words, what is providing the force. If I drop a pen, what's the agent of the force?
Gravity.
Okay, it's not gravity. Gravity is, no. Okay, raise your, I want to see, somebody raise your hand on this one. See,
Depends mass.
well, that's not the word, not the answer I'm looking for right now, but it's actually
Potential.
not a bad answer. If I let this thing go, what's the agent of the force? It's not, gravity is not the correct answer. Gravity's not a thing. Gravity is a description of a type of force.
So is it about depends mass?
I'm confused, are you talking about what stops it?
No, when it's in the air.
Oh.
Yeah, when
It's
it's in the
potential.
air.
It's potential.
Air force.
Okay, I get two, you gotta raise your hand. I'll call on you. Yes, sir. No, potential energy is more complicated. We'll talk about that. That's not it. What is, if I'm holding this pen, the agent of the force that's pushing it up is my hand. My hand is pushing on the pen. Yes, ma'am. No,
Is it the earth?
it's the earth,
Oh.
right? Okay, do you see that? If the earth weren't here, right, if we were just conducting this, if I were just conducting this class in space and we were floating around, I let it go, nothing would happen, right? Okay, so it's the earth. How do we know it's the earth?
Because
You can tell you can tell.
All right. So in other words, for a force to exist and to be real, you have to be able to identify an agent, right? We'll talk more about what the specific kinds of forces are, but like what would happen, for example, if I were to, well, let's say that I had a spring attached to a wall and I pulled something back and I let it go. Well, what's the obvious agent of the force? The spring, right? Okay, what if can anybody give me an example of, well, no, you won't. So what about this? What if we do this? How many people have been on the ride? I don't know if it's ever been, probably not the penalty, but you've been to a fair, when you've been on the ride, you know, one where it spins around and you stand against the wall.
Like the platform you're against goes up.
Yeah.
It was
And then like
the
the
gravity
gravitron.
spin is like.
The gravitron, I don't know what it's called, but here's what it is. Here's what it is. So you get in this big tube essentially, and there's a floor at the bottom, right? And it starts to spin. Starts to spin around real fast, and then the floor drops away, and you can see the pavement below you, right?
Yeah.
Is that the one you've been on?
I ain't going on.
Yeah.
Hey, look, but there's still a floor. I mean, it goes up in the air, but
I
there's
thought you
still
were
a
talking
floor.
about the gravitron where it spins and you're against these like platforms.
That's
you stand
basically
against
what
them,
it is.
and then they move up on the wall because of the floor.
That's the spaceship 2000.
Oh, that would be the same
Like
concept.
it
Yeah,
pushes you
that's
against the
awesome.
wall.
Yeah,
Like if you try to lift your head up, it's like
There's
still
still a floor.
Okay, do you
That's
everybody understand
dangerous.
what I'm talking about here? I'll tell you what, let's do this. Okay, so even if you haven't ridden on that ride, just imagine, take a second and imagine what that would feel like, right? You'd get squashed against the wall, right? You'd feel pressure against the wall so much that your friction against the wall would hold you in place when they dropped the floor and you wouldn't fall down. You probably feel some pulling on your back a little bit, but that's kind of just close your eyes and picture that, right? So that feels like a force, doesn't it? Right? For sure, that feels like a force. What's the agent of that force? Okay, rotation is not a thing. So it's got to be, you have to be able to attribute, the agent has to be a thing that you, like the earth is the agent if I drop the pin. My hand is the agent if I support the pin. What's it going to be?
Would it be like moon orbits the Earth, and it goes really fast, it's gonna keep getting wider and wider out, and eventually it would just slingshot away.
Okay, it's-
kind of like that.
I mean, it's a very similar situation.
Is it the thing you're standing against?
Okay, what's pushing you out against that wall? Is my
It's
question.
It's like kind of like when you're in a tornado, and if you're in the eye of the tornado, there's like no air at all, and then if you're like the actual tornado,
We stood very similar, I think.
yeah, like if you're in the eye of the tornado,
Okay,
like right.
hey, listen, this isn't working. We gotta raise our hand. That's, okay, so that's a good example of something similar to this. But do you agree that it feels like something's pushing you out against that wall, doesn't it?
Yeah.
Right? Okay, what do we call that force, do you know?
Centrifugal.
Centrifugal, right? We'll talk more about this later, but I tell you what,
Is it like creating its own center of gravity?
you guys, for all of you that think that was a force, you just got served. That's not what it is. It's
Oh.
not a force. Because
That's what I said.
you can't identify an agent. There is none.
So it's technically not real.
It's not a real force. It's something different. There is no force pushing you outward. There's not. It feels like it, but it's a fictitious force. And the way that, for now, all I'm gonna do to prove that to you, we'll talk more about this later when we talk about rotational motion. Because there are some forces going on there. But there is no force pushing you out towards the wall. None. If there were, think about that. There would have to, how would it cause that? You'd have to have some ring of super high density material outside of the ride that's gravitational. Obviously, that's not it, right? What else could it be? Could it be like there's some charge that's, well, no, that can't be it either, right? We'll talk about charges and you'll see why that couldn't be it. There can't be any agent for a force like that. It's impossible. There's nothing that could be pulling you outward radially, so your direction's changing, right? But you're always, whichever way you have to be pointing from the center, there's some kind of a force pulling you against that wall. That should kind of not sound feasible, right? So there's no agent, so that is not a force. Centrifugal force is not real. Yes, sir.
What's the difference between centrifugal and centrifugal force?
Same thing.
Same thing?
Yeah, it's just pronounced centrifugal. They're spelled the same word.
So how is it called a force if it's not really a force?
It's because it's called a force because it's useful sometimes to think of it like a force. Like, for example, if you wanted to create a space station, right? A real problem with astronauts in space is that they die a slow, miserable death because their bodies are not subjected to forces, and so their bones atrophy, their muscles atrophy. And if somebody is going to live on the International Space Station for a year or something, well, they're actually going to shorten their lives a little bit by doing that. So that's kind of a sacrifice because their bodies are going to deteriorate. They're going to lose bone mass that they'll never be able to get back. They're going to, their vasculature changes, their muscles atrophy. It's not a good thing. So they have to constantly be, they have to like an hour a day kind of a thing, be doing exercise to try to limit that effect as much as they can. But it's a real issue. Okay, but if you wanted to build a really big space station, there would be an easy way to get around that. What would you do? Spin it. Yeah, you could make it like a bicycle tire, right? Have everybody live in the tire, and it spins around, and that force, it's just not a force, right? It's not real, but it would be useful. And so we call it a force because it acts like a force. It's not really a force. What's really going, I'll give you just a little hint. What's actually going on there is that the force is being provided by the wall. The wall is changing your direction, and so it's providing a force. But we're not quite ready for that yet. We'll get there soon.
So it is
We'll get there
force.
soon.
It's like when you.
No. But the force that's acting is not pushing you out, it's pulling you in. It's the opposite.
So it's like kind of a car rash. Never mind. Car rash.
Okay. Yes, sir.
So that situation that you just said, where the space station would be spinning, would people walking in the space station have any effect on it spinning since they're pushing off?
Well, I mean, but assume that the mass is really big and it's negligible. Yeah. I mean, we have a technically. Okay, close your eyes and really concentrate for a second. If I walk towards the door, did you feel it? Did you feel the earth roll back just a little bit? Because it did a little bit. You probably don't notice it, right? Okay, so.
So it has to do with like your inertia. But,
Yeah.
But there's no actual force.
Well, I know it's not very just hold, it'll make sense for us to talk about that in much greater detail very soon, and then you'll have a thorough understanding of it.
Fine, very
I
soon.
know, but I just always hear what you're going
In less than 10 years, no. All right, so what I want to talk about next then is let's kind of try to describe a force, right? So I'm going to just do a little experiment here, and I want you to kind of see, this serves a couple purposes. We're going to do some work in the lab here very soon, like next week. And so I want you to kind of get an idea how to use this equipment, first of all. So what I want to do here, I'm just going to pull this stuff up on the screen, and you're going to watch. So okay, so first thing you want to do,
Shut up.
okay, so first thing you're going to do is when you go to the lab, is you're going to log into the computer, and you're going to look for Logger Pro 3.9. If it's not there, we're going to have to, I'll install it before you get there. I'll check. It should be there. So you're going to boot up Logger Pro 3.9, and it's going to pull up something like that. But then what we're going to do is I'm going to have you open up a specific lab. So you rarely ever have to actually set this computer setup here, which is it's the LabQuest Mini is what we use as the interface. You rarely ever have to set this thing up to record something manually. You can almost always rely on a template. And the templates are, if you want to go to those, you go to File, Open, and then it'll take you into this folder, which is all the vernier experiments that are kind of canned experiments. We want to go to physics with vernier, and like today, I would probably tell you guys for this one to go to card on a ramp, for example. Okay, so I'll go to card on a ramp, and then it'll pull this up. But it's going to tell me that this lab is associated with a certain sensor, and it's not hooked up. And so then what we would do is we would take this, for this one we would be using the motion detector, and all you'd have to do is plug this into one of the digital jacks on the side. And when I do that, it's all set up. Okay, it knows. And so now I'm ready to collect data. Okay, but before I collect data, a couple things I want to do here. So now is where you want to get where you can see pretty well. So you can even just stand up here if you want to. Okay, so I've got this. This is all this stuff is so ridiculously expensive you can't believe it. So you got to be very careful with it. This is an extruded aluminum track, very high quality. You can attach, it's really well made. You can attach all of these, like in this case, the feet, they just go into these channels. There's like a little screw that goes in there and you can tighten it. You'll see when you mess around with it. But then this allows me to level this thing. I forgot to bring the bubble levels, but I'll bring them next week. But you can even do it this way. You can even just take the cart and you can see that right now it's not level, right? It's definitely going downhill that way. So I'm just going to go through the process of kind of trying to get this thing set up. You can go down a little bit maybe. And before you know it, you got yourself a level track. Okay. And the way you really can tell is if you just put it in the middle and you tap it one way. Stops, tap it the other way. Okay, it's still going down a little bit too far that way, isn't it? Right. It's very scientific. Okay, it still wants to roll that way a little bit. Well, we're getting better. Okay, that's pretty good. That's pretty good. Okay, so here's our cart. I'm going to set this up, so we're going to do a couple things. I'm just going to pull this with a rubber band, and we're going to measure the motion when I pull it with a rubber band. So we're going to get this guy set up. So I'm going to put it at this end, down here. And what this is it's an ultrasonic, you'll hear it kind of click when we do this. It's got a little piece of foil in there that's going to vibrate, and it's going to send out sound waves, and they're going to bounce off of an object, and then it's going to return to to the detector, and the amount of time it takes to do that is going to determine where it is at that time. And so by taking a bunch of samples really rapidly of the position, we can do things like calculate velocity and acceleration also, right? On here, you notice that when you open this thing up, there's a little switch in there, and on the left, it's got a picture of a cart. On the right, it's got a picture of a person or a basketball, okay? So we want cart. Cart means we're looking at a smaller target, and you just have to kind of mess with this a little bit, and before you know, you got it working. So when I hit somebody, Lincoln, you be my assistant here. Just don't let that thing roll off the end. Just kind of catch it when it gets to the end. So on the screen here, notice where it says collect. Watch what happens when I what it did. Okay, let's look at that for a second. What did that just graph? Got 3 graphs in parallel here. Yeah, I mean this looks an awful lot like those pictures we drew, doesn't it? Right? We've got the position, which is measured from here. The position is increasing. And what do you notice about, it looks like right here is probably where Lincoln stopped it, right? Okay, what do you notice about that trip from here to there? A couple things. Okay, it's constant speed, constant velocity, I guess we can say. It's going in the same direction. How do you know it's constant velocity? Because, yeah, the slope is constant, right? So we could calculate the velocity from this graph by just looking at the slope. We've got the velocity graph right here, and it looks about like it should, doesn't it? It looks pretty constant. It looks like it slows down a little bit. How come? There's a little friction, and maybe I didn't get the the track perfectly level. Probably when you're doing a lab, you'd want to level it, spend a little more time with it, maybe. But this is not that big a deal today. What do you notice about the acceleration? It's about 0. Yeah, which makes sense, doesn't it? Nothing's pushing on it, right? It's just coasting. Okay. All right, so what we want to do, we want to answer a couple things then. We want to determine what is the relationship between the size of the force and the acceleration, for one thing. Okay, that's one relationship we want to explore. So what do you think I could do? Like if I take this rubber band, let's say, what if we do this? So I'm just going to tie this rubber band onto this little post here. And I'm gonna pull with one rubber band, and then I'm gonna pull with 2 rubber bands. And I want you to make a prediction about what's gonna happen. And I'm gonna, I forgot my little weights. Okay, hold that thought.